Dear students, we have seen in our last topic how to use an MNIST data set for the purpose of classification. We just saw how to load that data set and classify that into training data set and validation, and doing a bit of pre-processing wherein you clearly extracted 60,000 input data and 60,000 labels. You have seen that we have done one hot encoding of the labels, and then now we have got our segregated training data set. Now in today's topic, we are going to see in that classification how do we build a model. Before we actually go directly building a model, there are certain steps that we are supposed to follow. So first thing is, let us try and understand how model building is possible here. So we have already known that we have taken those input images and we labeled them at X, right. So we took X as the input. Now based on this type of X, there are several ways in which you can build a model. First, that we will look into. So if it is a single input scalar, then very easily the model will be expressed as this. Very simple. You have seen this, right? You came across this in simple linear regression also. So if X is a single input data, scalar data, then you can very easily build a model by using Y is equal to X into the weights plus bias, okay. But suppose if X is a multi-input single output model, there is a single output, Y is single, X are multiple, then what you can do, you are having multiple inputs and multiple weights. There is a single bias always, okay. So now how do I write X? X is a set of inputs. So what I am writing, say DIN is the dimension of the number of inputs. So I have X ranging from X1, X2, so on up till Xdin, right. And based on that I will have W1, W2, so on up till Wdin. DIN is what input dimension that I am referring to. So now what do I write? I have to now go back to this equation. Now I have X as multiple inputs and weights also multiple in nature. So what I am going to write here is Y, which is still a single output, is equal to weight into X, okay. Now that I have it vector, I can't have two row vectors multiplied with each other. So for ease of processing, I write it as weight transformed. So whatever row form it is, it will come as a column format, and then multiplication is easy. So I can't modify my input, but I can modify my weight. So weight transformed dot product with X. X is this, which is combination of so many inputs, and then you have a single bias. So you can even write it in this way. You have W1, W2, W3, so on. You can put it in this way, and dot product X1, X2, X3, so on, plus B. Always remember there is only one bias. Weights can be as many as the number of inputs. So this is the representation for your inputs. So by combining, multiple multi-inputs, if you have multiple multi-inputs and single output neuron model, that means you have single output for multiple inputs in one case. Again you have single output, multiple inputs. Again you have single output, multiple input, right? These three cases for an example, multiple input, single output. Now when you combine such cases, then at the end what you will get? You have multiple input, yes, so I get a multiple input model. You have single outputs for everybody, but then when you combine them together, you get a multiple output. So if you want to create a multiple input and multiple output model, the inference is you have to combine many multiple input single output models, okay. So by combining multiple multi-input single output neuron models, you can actually build a multi-input multi-output model. The representation you can see is this. So you have Y and W and capital X plus small b. So here you have multiple outputs, multiple inputs, associated multiple weights, and then a bias. So there are these dimensions that I have mentioned. X has got a dimension of DIN, data input, B will be equivalent to the dimension of number of outputs, data output, Y is the total number of outputs relevant to dimension of outputs, D out, and weight matrix will be a square matrix of dimension D out by D in. So, this will remain throughout any classification problem relevant to images that you are going to solve. Okay. So, this is a uniform way of building a model. So, please make sure the dimensions of X, bias, outputs and weights you keep in your mind whenever you are writing your theory exam or whenever you are trying to do some coding. So, these all things should be matching. So, this is the way in which you can build a multi-input and multi-output model. So, you have seen what happens when the input is single input scalar, how should be the model. You have seen what happens when you have only multiple input and a single output, how should be the model. Then what happens when you club all multiple inputs and single outputs to build a multi-input, multi-output model. Now, we also write a multiple output and batch training model as this particular format. Okay, y is equal to x at w plus b. So, if you are dealing with batch data, then the dimensions will be like this. Input will be having din but an associated batch. So, now it is a matrix of dimension b by din, and bias is again relevant to the output dimension, and output vector is again dealing with the batch size and output dimension, and this is weight. Weights is always, weight vector is relevant to input dimension and output dimension. So, din represent input dimension, d out represent output dimension. X is always having the shape of b comma din. This b, you please do not get confused with bias. This b here is nothing but batch size. If you are dealing with a batch size data, batch means a simple sample out of your training data set. So, x has the shape of here now not only din, earlier we took entire samples at a time, so we were calling din. If you are dealing with batch wise data, then you have now x in the shape of b comma d in, where b is the number of samples in the batch and d in is the length of each and every sample. W, weight, is always having the shape of d in comma d out. So, the number of parameters that weights have, the number of weight parameters will be d in by d out. Bias vector always have a shape as discussed d out. Now, what is this at the rate symbol? So, if I just go back, these two are nothing but matrices, right? X is of the shape b comma d in. This is the shape of X matrix, and for W matrix it is of the shape d in comma d out. So, you make sure that this and this are matching so that you can go for a product of it. So, this at the rate here is nothing but matrix multiplication. Okay. So, since the result of an operation of x and w, x at the rate w is again a matrix. So, if you just go back, what should be the shape of this particular product? It will be what? B comma d out. So, it cannot be directly added to the vector b. Now, you go back, just see, if you multiply these two, x is of the value b by d in, w is of the value d in by d out. So, the resultant of this is going to be what? B by d out, right. Now, this b is nothing but your batch size, and this part that you are adding it to the model, it is nothing but the bias. Bias is always having the size same as your output dimension. Okay. So, now those two cannot be directly added. That is why what you must do is, you must have a platform that supports broadcasting. Now, what is broadcasting? It is simple like this. Suppose if you want to add 1, 2, 3, 4 to 1 and 2, how do I do that? So, you have to have a broadcasting platform here. Broadcasting may what happens is, suppose this particular tensor, it will just look at the higher value, higher dimension to which it is getting added, and it just broadcasts itself and give you the result. So, you get 2, 3, 5 and 6, okay. So, broadcasting is possible in tensors. More on it we will be studying when we will study tensor flow in detail in second unit. So, I am not going more on it. So, whenever, remember that if you have two matrices that you are getting adding here where the dimensions are different, then that is not a problem here, because TensorFlow supports broadcasting. The lower dimension data will replicate itself and get it added. So, it will not create any error for you. So, even though in our previous equation here, these two elements after multiplication, they are of different dimensions, but yes, addition is possible and getting an output out of it is also possible because of broadcasting. That is what I mean to say here. And if you want to build a neural network out of it, then here you have got, for an example, say 3 inputs x1, x2, x3. Then what are you going to have? You are going to have its associated weights, okay. Say you have two outputs O1 and O2. So, how much weights are you going to have? First input with respect to first output. So, you have W11, and second input with respect to first output, third input with respect to first output. So, with that you have here this first, when I write here W11, this represents for input and this represents where it is going as an output. So, here I have two outputs and three inputs. So, here I am getting weights as W11, W21, W31 corresponding to the first output. In a similar way, when you have for the second output, you will have W12, W22 and W32. So, in this model, you try to justify the dimensions that I told you. Here you have 3 inputs, 2 output dimension, 3 is the input dimension. What is the dimension of the weight matrix and what is the dimension of output matrix, input matrix and the bias. You just make a note of all these things. So, this is for your understanding purpose only. Now, let us build a model for MNIST data set. Now, how do I build? Now, we know that we have got grayscale images, right. So, all these grayscale images I told you, they are stored inside a matrix of shape H comma W, okay. Suppose you are using a batch of pictures, okay, then B pictures will be stored using a tensor of shape B comma H comma W, that I already taught you, right. Now, our model or our neuron model cannot accept, can accept only vectors. So, suppose you have this matrix H comma W, but you require to flatten it before you actually use it inside your neural model. So, you have to flatten it. Say suppose you have matrix here 3 by 3, 0, 1, 2, 3, 4, 5, 6, 7, 8. It is a 3 by 3 matrix. You cannot directly use that into a neuron model that we are building, a simple neuron model that you are building. You require to flatten it. So, once you flatten it, you get it as a vector and then you can use it inside your model. So, the length of the input features will now be the dot product of H and W. So, even though you are representing, you are thinking that an image is a row by column pixel image, but you have to necessarily flatten it to give it to a basic neuron model. Now, the output can actually be set to a set of vectors with the length d out, which is as same as the number of categories. So, here if it is an MNIST data set, we have categories, there are many images which are handwritten. So, 0, 1, suppose 9 and 3 and you want to label them as correctly, this image is of 0, this image is of 2, this image is of 3, so on up till 9. So, in that way you have got 10 categories for your MNIST data set that we are talking on. So, you will be setting it to a set of vectors with a length of 10 only, which is why it is important, because you are using one hot encoding. I will show you how. For an example, if the output belongs to the first category, then the corresponding index is set to 1 and the remaining all positions are set to 0. This particular method is called one-hot encoding. I'll give you a very simple example of one-hot encoding here. In place of taking MNIST dataset, here I have taken 4 classes. One is a cat, dog, fish and a bird. So, suppose this particular input images, you are supposed to categorize it into cat, dog, fish and bird. You want to label them. So, suppose this picture is of cat. So, only the first significant bit will be 1, remaining all are going to be 0. Second category mein second significant bit will be 1, remaining all will be 0. For the third category, third significant bit is 1, remaining all 0, and so is for the fourth category. So, if I talk on MNIST data set, you have categories as 1, 2, so on up till 9, that means 10 categories. So, you will be having, say for an example, 0, 0, 0, 0, 0, 0, 0, 0. You know, it's vice versa. Either you give LSB or MSB, doesn't matter. Suppose if I am giving MSB. So, you have now 9 as your length of output. The first significant bit is 1. That means this is the category of 0, which is 0. Suppose you want to categorize it as 1, then you will write it as zeros and all zeros. You want to categorize this particular image as 2. So, you will write 0, 0, 1 and all zeros. So, in that way till you reach to the category of 10, you will be categorizing it as in this way. This particular encoding is called as one-hot encoding. So, I am just teaching you this with respect to an MNIST model, but I am giving you lot of generalizing idea. How should be a model for single input, how should be a model for multi-input single output, how should be a model for multi-input multi-output, and if at all you are using multi-output, then those output categories should be one-hot encoded. And also if it is an input matrix that you are giving it to the neuron model, before giving it you please flatten it and then give it. Okay, that's how you are working here with this particular model. This was about building a model. So, it's always like you identify inputs, you identify the type of model, multi-input, multi-output, then you get your suitable training data and test data figured out properly, your output data should be categorized properly and properly encoded. Here I am using one-hot encoding, and then later what? So, what is the next step? The next step will be to identify the error function, and that we are going to see in the next topic.